Ramanujan is famous for somehow computing the values of divergent series. And to make sense out of what's really going on, we need to explore the concept of analytic continuation. And it's not a bad idea to introduce the concept with the simplest yet most meaningful example. You may have learned the geometric series formula in high school, but it only converges for any values of z with an absolute value less than 1. For example, let's take a number exactly on the boundary, like I. Then in this case, the sum oscillates forever and never converges to a specific value. And for any number outside the boundary, the sum blows up to infinity. But if we extend the domain of the function in a way that remains complex differentiable, there is a unique extension that is defined for all complex numbers except for 1. And that unique continuation happens to be 1 over 1 minus z, which has a singularity at 1. So the sum of powers of I itself diverges as a series, but its value makes sense over the analytic continuation. Now, let's take a look at the sum of powers of 3. There is a sense that this series actually converges. Let's rewrite the left side using base 3 numerals. And let's concatenate the sum into a single base 3 number with infinitely many trits. But for all practical purpose in this video, we only have 3 fingers. Then we can multiply both sides by 2, and we want to show that this number plus 1 indeed is 0. We can add the 1's digit, and 3 carries over to the next digit. And we can do the same for 9's digit, and 27's digit, and this continues on forever. So in some sense, this infinitely many digits of 0 actually is 0. So we have sorta confirmed that the extension formula works beyond the traditional radius of convergence. Now, the number system where this nonsense business formally works is called the p-adic numbers.